Hello, class. Okay, so we're going to talk about kinematics again, but we're going to look at plots. So to start out with, we're going to look at what we call an xt plot. So we're going to plot the position of a particle as a function of time. So we're going to start out with a very simple example. So I'll put a few, we'll just say, okay, so simple example, I'm going to draw an xt plot that looks like this, just a horizontal line. So we can say that this represents the position of an object as a function of time. And the question is, what is this object doing? And the answer is not very much. Like if you look at t equals 0, where is this object? It's at x equals 3 meters. So it's 3 meters from something we're just calling the origin. And if you look, say, a second later, where is it? Well, it's still at 3 meters. So basically, this thing is not moving. It's just sitting there doing nothing. Okay, so kind of a boring example. But let's look at a different example. Let's say we have a plot like this. So now at t equals 0, it's somewhere. It's at 1 meter. But then you look at a different time. Now its x coordinate has increased. So this is an object that is moving in the positive direction. As time increases, x increases. It keeps getting farther away from the origin. And so it's moving in one direction. There's more that we can say about this, though. I want to redraw this. Actually, I'm going to make a table as well. Let's say time and position in meters. So we go up to 4 seconds. Let's say 0, 1, 2, 3, and 4. I'm going to actually put numbers in. Let's say it starts at 1. And let's say after, I can't have it. Let's do this. And I'm going to actually plot these points. So at t equals 0, we're here. X equals 1. And then we're at 1.5. And at 2, we're at 2. 3, we're at 2.5. And then at 4 seconds, we're at x equals 3 meters. So again, we have this plot that looks like this. And obviously, this object is moving, because its x-coordinate is changing at time as a function of time. But we can say more than just the fact that it's moving. Overall, let's calculate the average velocity over a couple intervals. So let's look at from 0 to 1 second. And then let's look at the average velocity. So again, that's delta x over delta t. So the change in x is 0.5 meters, and the change in time is 1 second. So we have 0.5 meters per second. So that's just the average velocity over this 1 second time interval. Let's look at another interval, say 2 to 3 seconds. So we're starting at 2 and going to 3. So delta t is 1 second. Delta x is 2.5 minus 2. Again, that's 0.5 meters per second. Let's try another one. Let's go from 0 to 4 seconds. So from 0 to 4, that's a 4-second time interval. And the change in x is 3 minus 1 is 2. And 2 over 4 is 0.5. So it seems that any interval we pick, we're getting the same average velocity. And the reason Why? Is because this is a straight line. And so we can say that this is a motion with a constant acceleration. Yeah, I mean, clearly the velocity is not changing no matter what time interval we pick. And the velocity is 0.5 meters per second. Let's look at this interval from 2 to 3 seconds. I'm going to draw a triangle here. So what we have on the vertical scale, we're going from 2 to 2.5. That would be delta x. And going from 2 to 3 seconds, that's the time interval. Remember, the average velocity is delta x over delta t. And so the velocity is given by, delta x, which is a change on the vertical scale, over delta t, which is a change on the horizontal scale. And that's just the slope of this graph. And so, kind of set up this table over here. Right now we're looking at an xt plot. And the slope gives us the velocity. Now, that's great if we have a straight line like this, but what if we have, I'm going to draw a different one here. What if we don't have a straight line? What does it even mean to have a slope? We're going to erase this table since it no longer applies to this graph. If you're just coming in or something. Okay, so what if we have a graph like this? Now, if the slope gives us the velocity, well, the slope of what? What's the slope of a curve? And we're going to stick to kind of a graphical definition. So let's look at one particular time. Now, what we can do is we can draw a tangent line passing through this point. And it would basically look like that. So the way we graphically draw a tangent line, if you just follow the curve itself, and then when you get to the point where you want to find the slope, just keep going in whatever direction you were going. So like if you follow the curve, you keep turning. But if you just do this and then just keep going in a straight line, that would give you the slope of the tangent line. So if we look at this point, that's our tangent line. I can use a different color. Say this is at time t1. And then at time t2, we're over here. And so the slope, the tangent line for that point at time t2 is going to look like this. And we can see that the slope here is greater, which means that this is a greater velocity. And, at t1, this is a lesser velocity. So again, we're going to stick to like a graphical interpretation of slope. And the reason, of course, is if we have like this curve described by some function, there is a way to find the slope at any point, but that requires calculus, so yeah, we just stick to these graphs. Now, I'm going to draw one more picture here. Oh yeah, so let me kind of redraw this one again. So we had like two tangent lines, one at this point, and then another one here, which had a greater velocity, greater slope. And so as time increases, as we're moving along this graph, we can see that the velocity is increasing. And so this is a positive acceleration. So I'm going to draw one more picture for this xt plot. I'm going to draw something like this. So again, the slope is constantly changing. But if you look at this region in here, this is going to be a positive acceleration. And then at some point, we're going to have a negative acceleration over here. And to determine the type of acceleration, whether it's positive or negative, we have to look at something called the concavity. where you look at, is the slope increasing or decreasing? So if we follow this curve, here the slope is negative, but it's turning positive and getting steeper. So here we have the velocity is increasing, and that's a positive acceleration. And then over here, the slope here is positive, but it's curving downwards. Like it's steeper here than it is over here. And so it's kind of curving downwards here, so that's a negative acceleration. And it looks like it changes somewhere around here. That's what we call a point of inflection, where the concavity changes. And it looks like there's another one over here where we go back to a positive acceleration. Now again, we're being pretty imprecise and just looking at the picture. Like here it's concave up, that's a positive acceleration. Just like follow it from left to right and see what direction the slope is changing. Like here it's decreasing, going from positive to negative, but then it looks like it's increasing again. So you can tell what regions, and again, we don't have to be very precise with that because you can't just from looking at the picture identify exactly where it changes from positive to negative. But just like in here, positive acceleration, and then a negative, and then back to positive. Okay, so that's what we can get from these xt plots. The main thing is that the slope gives you the velocity. Now, I want to draw another kind of plot. And that is looking at velocity as a function of time. And we're going to start out with another very simple example, just a horizontal line. Okay, so we've got this horizontal line, and let's just look at it over this 5-second interval. So we're describing an object here. This is the velocity of this object, and we can see that at least we're moving in this case. We're moving at a constant rate of 3 meters per second because you look at any time on this interval, you check the velocity, it's always 3 meters per second. And so this is a constant velocity. Which means no acceleration. If the velocity is not changing, that means no acceleration. Okay, and let's look at a numerical example. Let's write down our kinematic equations. We probably don't need all of this room for the table. I'm going to write the first one like this. So normally I write it x equals x naught. If I subtract x naught from both sides, we get the displacement on the left side. And here's our velocity as a function of time. Okay, so we've got zero acceleration in this case because we can see from the graph it's a constant velocity. And so we can see in this case, very simple result, that the displacement is just the velocity times time. So let's look at this entire 5-second interval and find the displacement over this entire interval. And here the velocity, the initial velocity is 3 meters per second. And it's moving for 5 seconds. So if we cross out the seconds, we get a displacement of 15 meters. Now, I want to draw a vertical line here. And we can talk about something called the area under the curve. So it's just like we have our line, and we want to find the area like between this line and the axis. And we call that the area under the curve. Seems obvious, but it's actually not necessarily as obvious as it sounds, because remember, we're applying the velocity of the time. That can be negative as well, so we'll have to consider that. But for now, a very straightforward thing. And let's look at the area of this rectangle. So in this case, we form a nice rectangle. And the area of this rectangle, and again, I want to include units. So remember, just base times height. So the base is 5 seconds. And the height is 3 meters per second. And so we get 15 minutes. And we can see that the area is equal to the displacement. So here we have I'm going to write area. So here we have a VT plot. And the area gives us the displacement. Now, if we go back to the XT plot and look at the area, I didn't even cover that. Imagine, here, I'll just erase this for now and then rewrite it. But if we talk about an XT plot, what are the units of area going to be? Well, remember, it's like base times height, so we multiply, we have seconds times meters. What is a meter times second? Does that, relate to anything we've done? No. Basically, there's nothing significant, at least nothing I'm aware of. Never seen a reason to find the area under an XT plot. That doesn't tell us anything useful I can think of. So, yeah, we just put a line through that. Okay, let's go back to VT plots now. So, velocity in meters per second. Now, I want to look at another example. Let's do... Now, in that case, we had a nice rectangle. What if we have something like this, though? So what if we have... This is a straight line again. I want it to end at 3 seconds, so it doesn't match up perfectly. But we have a straight line in this case. And we can find the area under the curve, but is that going to be equal to the displacement in this case, if it's not a horizontal line? So there's kind of a couple issues here when you don't have like a horizontal line. One, in general, you could have a velocity time plot that maybe looks like this, and then how would you even find the area underneath this? If this has some, non-linear shape, that's a difficult problem. That's something we can't do. Now, again, calculus, as long as you know the shape, you can find the area under a curve. That's a very classic calculus problem. One of the reasons calculus was invented is to find areas underneath curves. But we can't do that in this class. But if we have this, a straight line here, we can find the area under the curve in this case. So let's do that. And the reason why is we can draw this horizontal line here and break it up into a rectangle and a triangle. Let's find the area under the curve and see what we get. Let's call this A1 and this A2. In this case, we do have an acceleration now, because the velocity is clearly changing. It's going from 1 to 3, so it's not constant, so there is an acceleration. And that raises another question: what is the acceleration? So let's start out with that. Let's actually find the acceleration. Now, I'm just going to state, because this is exactly what we did earlier with XT plots, because it's a straight line, this means a constant acceleration. We can take the slope over any interval, and it's going to be the same thing. And so, yeah, basically the acceleration is delta v over delta t, and delta v is the change in the vertical scale. So let's just look at this triangle here. Delta v would be like 2 meters per second. If we're looking at this entire time interval, and there's 5 seconds. So again, very important to pay attention to units. on the vertical scale, we're going from 1 to 3, so that's a change of 2 meters per second, and then over 5 seconds. So this is 0.4 meters per second squared is the acceleration. And we can see delta v over delta t, that is the slope. So I'm going to write that down over here. The slope gives us the acceleration. So on an xt plot, the slope gives you the velocity. In a vt plot, the slope gives you the acceleration. Now, you might think, how am I going to remember all this? Well, you don't have to. Just remember that the slope and the area under the curve, they can both have a significance. Not always, like in the xt plot, the area, I never find anything useful about that, but the velocity does. And it's very easy to determine what thing you're talking about just by looking at the units. Like if we have an xt plot, if we look at the slope, remember we're looking at like this triangle where we have a change in the vertical scale over the change in the horizontal scale. So this would have units of meters per second, which is velocity. In a VT plot, we look at the vertical scale, which is meters per second, over seconds. That's meters per second squared, so we know we're dealing with acceleration. Similarly, if we want to find the area underneath the curve, we're going to multiply these two scales. Think of this rectangle. The area is going to be the base times the height. So we're going to have seconds times meters per seconds, which is meters. So that's giving us the displacement. So you don't have to remember these things. Just think of the units. So slope, vertical, over the horizontal, and area, vertical times horizontal. And from the units, you should be able to tell what kind of thing we're talking about here. But let's go back and find the area underneath the curve. So let's start with A1, which is just a rectangle. I think I can do this here. So that would be base times height. We have 5 seconds times a height of 1 meter per second, which is 5 meters. And then if we look at A2, the area of a triangle is 1/2 base times height. So we have 1/2 times 5 seconds. And then the height, we're going from 1 to 3. So the height is 2 meters per second. And the seconds cancel out. So we get 5 meters again. We have a 1/2 and a 2. They cancel out. So A2 is 5 meters. So the total area underneath this curve is 10 meters. Okay. Now, does that represent the displacement like before? Well, we can check this with our equation. Let's calculate the displacement. So we've got this first term, which is V naught T. V naught is 1 meter. I'm sorry, 1 meter per second. And then times 5 seconds. Notice that that is literally just the area here, A1. 1 meter per second times 5 seconds. And then A2, or the next term, we have 1/2 times the acceleration, which is 0.4 meters per second squared. I'm going to do it this way. Yeah, the acceleration, I'm going to write this as 2 meters over 5 seconds squared. And then times t squared, which is 5 seconds, in parentheses squared, so that'll be 25 seconds squared. So, yeah, just squaring t. So these cancel out. Here, this one we've already established is 5 meters. And here, these cancel. 25 over 5, that is also 5. And second squared cancel. So we get 5 meters, which is that. And so, yeah, this still gives us the displacement. The area underneath this curve still gives us the displacement, just like it did for the constant velocity case. And if we can establish that's true for rectangles and triangles, you'll see if you take calculus, or if you have taken calculus, that you can approximate, or you can not even approximate, but actually it's by definition, the area under a curve, well, yeah, you can approximate this to any accuracy you want by kind of breaking it up into like areas and triangles. So like, if you want to find the area under a curve, you'd break it up into these trapezoids, for instance. And you could find like the area here and the triangle. And by making these, by increasing the number of trapezoids, like just making it a finer division, you can get more and more accuracy until you get like an exact result using calculus. So if you can establish, like we did, that this works for rectangles and triangles, in calculus you can do that for any curve, basically. So whatever the shape of the curve on the VT plot, the area underneath it gives you the displacement. And finally, we want to look at an acceleration time plot. Acceleration in meters per second squared, and time in seconds. So we're going to do two things. Let's start by looking at the slope. Just the units that we get. So remember, the slope is a change in the vertical scale. That'd be meters per second squared over a change in the horizontal scale, which is seconds. This is meters per second cubed. Now, does that sound like anything? And actually, this does describe something that has a name. It's called a jerk. Picture like, grab a rope, like jerk a rope, and it just causes like rapid, this would actually be like a change in acceleration. It's a very kind of abrupt movement. So, yeah, it's not something we deal with in this class. So for the acceleration time plot, for the slope, even though that does have a meaning, it's not something that we talk about in this class. Remember, we only consider a case of constant acceleration. So the slope, the only case we'll consider is a constant acceleration, which is that horizontal line. So the slope is 0 anyways. So we don't care about the slope, even though that could have some physical significance. For this class, we don't worry about it. So let's just say this is some constant acceleration, and we're going to look over some time interval. What about the area under the curve? Let's look at the units. So remember, we multiply the two now. So we have meters per second squared times seconds. That is meters per second. And so those are units of velocity. So do we write down velocity here? And the answer is no, not exactly. Because if I ask you, like, let's put numbers here. Let's say this is 3. 3 meters per second squared, and this is 6 seconds. So with this information, do you know how fast this object is moving after 6 seconds? And the answer is definitely no. And again, real quickly, let's calculate the area anyways. So we have 3 meters per second squared times 6 seconds. So that's 18 meters per second. That's something related to velocity. But the thing is, we don't know what the initial velocity is. So without knowing how fast it was moving at the start, we know that the acceleration is a change in velocity, and that's what this is. I'll just write delta V. So the area gives you the change in velocity. Okay, so we covered the very basics here. And I think I'll leave it at that because there's a few things that we could still consider. Like, what if we have a plot that, here, let's go back to like a velocity plot for a moment. And, we already knew how to handle that. But what if we have something like this, where it, starts out positive and goes negative? Like, what does area even mean here? And I think we'll save this for our review, where we'll do a problem just like this. So I'll have a problem with a VT plot, and, what does this area represents? Or how do we even calculate that? But I think that'll be better to do in the context of like a concrete problem. So we'll save that for the review. And yeah. So I think we covered the basics, and I'll just stop this video